Hi everyone, welcome to the HKN video tutorial for Fourier Series. The main concept behind Fourier Series is given by these two equations here. What we want to do is take a periodic function in the time domain given by small f of t and decompose it into an infinite sum of weighted exponentials. And in this way we decompose it into the frequency domain. And in order to find the values of these Fourier series coefficients given by capital F of n, we can evaluate this integral given here, 1 over t, where t is the fundamental period of the function, times the integral over 1 period of small f of t times e to the negative j omega naught nt, where omega naught is the fundamental frequency. And for this video, we're going to go over a little example and find the Fourier series coefficients for this function given here, little f of t. And you can see the piecewise definition of this function in the bottom right hand corner. And right away we can see that the fundamental frequency omega naught is given by 2 pi over the fundamental period. And since the fundamental period is 2, since it stretches from -1 to 1, we can see that omega naught is just pi. Okay, and to start our derivation of the Fourier series coefficients, we can write down the general form of the integral. And since it's a piecewise function, we can into two parts, going from -1 to 0, and another integral going from 0 to 1. And we'll take these integrals one by one and then combine them at the end to find the overall expression for f of n. For the first component, for both of these components, we're going to want to do integration by parts. This is going to be a common theme that you see for Fourier series derivations, and it's a good idea to have this down pat. And so as we've learned in calculus classes, the form for integration by parts is integral of u dv equals uv minus integral of v du. And for our example, here's a decomposition that you can do to evaluate this integration by parts. And we won't go over all the algebra, but we see that in the end what we get is that the first component of the integral gives us j over n pi plus 1 over n squared pi squared minus 1 over n squared pi squared times e to the j n pi. And similarly for the second portion of the integral, we can use integration by parts, and we get -1 over n squared pi squared e to the negative j n pi minus j over n pi plus 1 over n squared pi squared. And if you have any questions about these derivations, just leave a comment. And so if we combine these two portions of the integral to get the overall expression for the Fourier series coefficients, we find that some of the terms cancel, the j over n pi terms cancel, and what we're left with is 2 over n squared pi squared plus this term and the final term. And we can use an identity. We see that e to the negative j n pi and e to the positive j n pi can both be rewritten as -1 to the n plus 1 power. And you can plug in a few values for n and see that this is the case. And this is going to be a very useful identity to keep in mind for Fourier series derivations, because this is useful for us to get the Fourier series coefficients in terms of even and odd ends. So what we see once we make this simplification is that we can rewrite it as 2 over n squared pi squared plus 2 over n squared pi squared times -1 to the n plus 1 power. And because -1 to the n plus 1 power is periodic, it goes from -1 to 1 to -1, etc. Oops. We can rewrite this in the case when n is even and when n is odd. And we see that when n is even, we get that the Fourier series coefficient is 0, and then when it is odd, we get 4 over n squared pi squared. And so a few values of these coefficients are given on the side. And the special case that we need to keep in mind is for f of 0, because this integral involves n in the denominator a lot, we need to treat this as a special case. And an easy way to find f of 0 is to find the DC component of our time-varying function. And we see that for our case, our little f of t is symmetric about f equals 1/2. So that means that our DC component of this function is 1/2. And therefore, we can just say that f of 0 is 1/2. And that is all we need to do to find the derivation of the Fourier series coefficients.